Episode 4, Inside the OS Brain, Kernel Architecture. Content begins. Welcome back. In previous lessons, we've viewed the operating system as a manager, a conductor. Today, we're going even deeper, right into the brain of that manager. The core component, the command center of every operating system, is called the kernel. So, what exactly is the kernel? Imagine the operating system is a government. There are departments that work directly with citizens, like licensing agencies and public services. Those are your application programs and user interface. But behind them, there must be a central authority that makes the highest level decisions, coordinates national security, manages the treasury, and ensures everything runs smoothly. That central authority is the kernel. In a computer, the kernel is the very first program loaded into memory when the system boots up, and it stays there until the system shuts down. It controls everything, from which task the CPU will process next, to how data is read from the hard drive, and how programs communicate with each other. Every request from software to hardware must go through the kernel. To perform this critical mission and to protect itself from potentially faulty application programs, the kernel creates two distinct operating spaces, kernel space and user space. User space is where your regular applications run, your web browser, games, office software. These programs have very limited privileges. Kernel space is a strictly protected area where only the kernel and its most critical components are allowed to operate. It has full, unrestricted access to all hardware. This division is like a bank. Customers, user space, can only operate in the main lobby and interact through tellers. They cannot simply walk into the vault, kernel space. The act of going from user space to kernel space to request a service is a special, tightly controlled action called a system call. And how these kernel brains are designed and structured internally is our main topic for today. There are two primary architectural schools of thought that have shaped the world of operating systems: the monolithic kernel and the microkernel. 1. The monolithic kernel architecture. Monolithic means made of a single, massive block. True to its name, in this architecture, all core services of the operating system, process management, memory management, file systems, device drivers, and network management are bundled together and run in a single address space, the kernel space. Imagine a giant government building where all ministries and departments work under one roof. When the Ministry of Transportation needs information from the Ministry of Finance, they just have to walk down the hall and talk directly. Advantages: extremely fast. Because all components reside together in kernel space, they can call each other's functions and access data directly, without any barriers. This internal communication is efficient and has very low latency. Disadvantages. Let's go back to the government building example. If a small department, say the cafeteria, catches fire, there's a risk that the entire massive building will have to shut down. Similarly, with a monolithic kernel, a small bug in a single device driver can crash the entire operating system, a phenomenon old Windows users know as the blue screen of death. Furthermore, adding a new feature or fixing a bug requires recompiling the entire kernel, making maintenance and development more complex. Classic examples of monolithic kernels are Linux and the Unix family of operating systems. The power and performance of Linux on servers largely stem from this monolithic design. 2. The microkernel architecture. In complete contrast to the monolithic approach, the microkernel school of thought has a simple philosophy. The kernel should do as little as possible, but what it does must be absolutely essential and perfect. In a microkernel architecture, the kernel brain is shrunk down to the bare minimum. It only retains the most fundamental functions: inter-process communication, IPC management, basic memory management, and basic CPU scheduling. So what about everything else, like the file system, device drivers, and network stacks? They are all pushed out of kernel space and run as regular processes in user space, referred to as servers. Let's return to our government analogy. Instead of one giant building, a microkernel government has a tiny, ultra-secure central office. This office's only job is to connect and relay information. Other departments like the Ministry of Education and Ministry of Health are independent agencies in their own separate buildings. When the Ministry of Education needs to work with the Ministry of Health, they must send an official message through the central office. Advantages: very high stability and security. If the server managing the sound card crashes, it will go down by itself, but the rest of the operating system remains perfectly stable. You might just need to restart that one server. This architecture is also modular and highly flexible. Want to upgrade the file system? Just replace the file system server without touching the kernel. Disadvantages: slower performance. Communication between the servers in user space must constantly go through the kernel's IPC mechanism. Sending and receiving these messages back and forth takes time and creates significant overhead compared to just walking down the hall in a monolithic kernel. Famous examples of microkernels include QNX, used extensively in automotive and industrial control systems, Minix, an academic OS that inspired Linux, and GNU Hurd. 3. The hybrid kernel, a compromise. In reality, the line between these two architectures is not always sharp. Many modern operating systems have chosen a middle path, known as a hybrid kernel. They generally follow the structure of a microkernel, but to improve performance, they allow some critical components, like graphics drivers or parts of the file system, to run in kernel space. This aims to leverage the speed of the monolithic design for performance-sensitive tasks while retaining the stability and modular structure of a microkernel. Windows NT, the foundation for all modern Windows versions from XP, 7, 10, 11, and macOS with its XNU kernel, are prime examples of this hybrid architecture. Conclusion. Thus, the choice between a monolithic and a microkernel design is a classic trade-off in operating system engineering: speed and performance versus stability and flexibility. A monolithic kernel is like a Formula One race car, incredibly fast and efficient, but a single small mistake can lead to a catastrophic crash. A microkernel is like a container ship divided into many separate compartments. It's slower, but if one container has a problem, the other containers and the ship itself remain safe. A hybrid kernel is the attempt to build a car that is both fast and safe by combining the best advantages of both worlds. Understanding kernel architecture gives us deep insight into the most fundamental design decisions that shape the performance, stability, and character of the operating systems we use every single day.